I'm very happy to start another edition of our seminar series. We're very happy to have Michael Becker from UMass Amherst, and Michael will be talking about phase transitions, dark matter, and black holes. Right?
Thank you very much. Yeah, it's a pleasure to be here. I last visited NYU about 5 years ago, but I started position at UMass Amherst, which isn't so far away, so it's nice to be visiting again. Right, today I'm going to be talking about phase transitions, dark matter, and black holes. I'm going to cover quite a few topics at quite a high level. There won't be too many details, lots of kind of cartoon pictures and trying to explain the ideas. But please ask me if you have technical questions, or I'll be around tomorrow as well. We can talk about anything in more detail that you'd like to ask questions today. So in my group, I work with Aidan Simons, who's a PhD student, and Joachim Igwafwan, who's a postdoc, who joined me he was at Annecy for his PhD before. Okay, the outline of the talk is, first topic I'm going to talk about is filtered dark matter, which is a relatively new dark matter production mechanism. That then led me onto ideas about primordial black hole production. It got me thinking about primordial black holes. And towards the end, I'll be talking about what we could learn if we observe an exploding primordial black hole. Okay, so the introduction is going to be in two parts. First, phase transitions. If you don't know about cosmological phase transitions, and then a little bit about dark matter, and then there'll be a third introduction halfway through the talk on black holes. So in the history of the universe, there are several cosmological phase transitions that theoretically we expected to occur. So when the temperature was around 100 GeV, there was the electroweak phase transition when the Higgs field obtained the vacuum expectation value and all of this elementary fermions and gauge bosons obtained their masses. There was another phase transition at around 100 MeV, the QCD phase transition. This was a confining phase transition where the quarks became bound into protons and neutrons and mesons. Then later, at a low temperature, around 300,000 years after the Big Bang, free electrons bound with nuclei to form atoms, and this is when the surface of blast scattering is, when the CMB is from. So this is kind of three examples of phase transitions where the bulk properties of the cosmos, of the universe, change quite quickly through a phase transition. And there's different kinds of phase transitions. Like I said, there's a confining phase transition here, but the electroweak phase transition is kind of spontaneous symmetry breaking. And that's the kind of phase transitions we're going to be talking about today.
Well, normally none of these phase transitions occur, right?
Sorry?
I mean, they're all smooth crossovers.
Right, none of these are first order phase transitions, or at least
So there are no phase transitions in electroweak theory, and QCD are common to column load.
Okay, so the bulk properties of the universe change relatively quickly. Exactly how that happens, we're going to be discussing this a little bit, and we'll talk about different types of phase transitions.
These are crossovers,
Right,
at least according to common load.
right, as far as we know. But as far as I'm aware, a crossover phase transition is still a form of
phase transition is something not continuous. So this guy is continuous.
Right, it's still the bulk properties of the
I don't know if that's the definition of a phase transition.
Sorry?
Normally you have some correlator, and that correlator has different properties, whether you're like in a
Yeah, I mean, it's basically they have first order phase transition if there is non-zero latent heat.
first order, yes, first order, but second order.
I'll specify the kinds of phase transitions that we're going to be interested in. There's a variety of times in the evolution of the history when the bulk properties of the universe have changed. So the electroweak phase transition, this is spontaneous symmetry breaking. So at temperatures much higher than the electroweak temperature, the Higgs field has no vacuum expectation value, but then at lower temperatures, it gains a vacuum expectation value. So as we've just been discussing, the standard model electroweak phase transition is a crossover transition, but we're going to be interested in similar kinds of spontaneous symmetry breaking phase transitions, but first order phase transitions of VSM scalars, not of the standard model Higgs field. So the way a first order phase transition proceeds, we have a little animation here. This is just a slice of space. And ignore the red, this is to do with gravitational waves. But these blue regions, this is where the vacuum expectation of the field is non-zero, and the gray region, the vacuum expectation field of the field is 0. So as time goes on, these bubbles expand, new bubbles nucleate, they merge, and then end up filling the whole universe. So this is kind of what we should have in mind when we think about a first order phase transition, is bubbles of the new phase nucleating, expanding, and finally taking over the whole universe. Okay, so that was just briefly about phase transitions. Now about dark matter before we put these two ideas together. So we know that dark matter is stable, at least on the age of the universe, the lifetime of the universe. We know it's cold in the sense that if it's a particle, it's moving non-relativistically. We know that it's dark or has at most very, very weak couplings to photons. We know that it's not part of the standard model. Neutrinos would be warm dark matter, which doesn't fit with simulations of galaxy evolution. And the abundance is known very precisely for a cosmological observable. It's known to about 2% accuracy. And there's an observation that the dark matter energy density is roughly 5 times the baryonic energy density. Now this raises a question as to, let's go back. Sorry. Raises a question, is there a non-gravitational interaction between dark matter and the standard model? Theoretically, we don't know. Observationally, this kind of coincidence between the dark matter energy density and the baryonic energy density has typically, for many people has suggested that maybe there are non-gravitational dark matter standard model interactions. And maybe a more pragmatic way of thinking about this is you can have a flowchart about whether you assume that there are non-gravitational interactions or not. If you pick no in your model building, then typically you reach a dead end and there's not much more to be done. Whereas if you choose yes, then you can calculate and you're away and you can do phenomenology.
Why do we know this is not in the standard model exactly?
Right, so the only standard model particle that could satisfy all of these, well, most of these conditions is the neutrino. So that's a neutral particle in the standard model. So it's stable and it's dark, but it's not cold enough. If you look at the mass of the neutrinos that would be left over from the early universe, then they would be what's called warm dark matter. And this doesn't seem to fit with simulations of galaxy evolution. So dark matter played a crucial role in the evolution of galaxies. If neutrinos made up the dark matter energy density, then you don't get the right formation of the galaxy structure. This is not part of the standard model. That should be interpreted as like none of the particles of the standard model. So people have recently been talking about primordial black hole dark matter. Those primordial black holes could have formed from standard model particles. So that is potentially a way that standard model matter could have been dark matter, is if it's in the form of black holes. And here I'm really talking about a particle description of dark matter. Okay, so this is, at least to my view, why one of the main reasons that people often assume that there's a dark matter standard model interaction, because then you can compute with it and you can probe it at collider experiments, direct detection, and indirect detection experiments. And typically you reach a bit of a dead end if you don't assume this interaction. You're not sure how it's formed and there's no real ways of testing it. We'll come back to this at the end of the talk though, and say maybe it's not as much of a dead end as that you may think. So we're going to talk about an observational way of probing a dark matter that doesn't interact with the standard model particles. But for now, at the beginning of the talk, we're going to take this yes route. So now we're going to be talking about a new dark matter production mechanism. So there's a clear question as to why would you be interested in a new dark matter production mechanism? So the favored production mechanism, thermal freeze out, which has been around for 30, 40 years. It's not been seen experimentally, despite a massive effort with direct detection experiments, indirect detection experiments, and colliders. So a huge amount of phase space has been, model space has been probed of these experiments. Much of it was expected, like sort of favored in many senses, and nothing has been seen. And this is motivated for people to look at a much wider range of dark matter candidates and production mechanisms. Another reason is that thermal freeze out, there's the Grease-Kamienowski bound. So this is the energy density of dark matter, which is known very precisely. Through thermal freeze out, this is expected to go as 1 over the thermally average cross section. And then you can do a partial wave analysis, and the couplings here need to be bound by perturbativity, which is where the 4 pi comes from. So that tells you that the 1 over the thermally average cross section has to be larger than this. And you plug the numbers in, and you find that dark matter produced through thermal freeze out has to be less than 300 TeV. So there's an upper mass limit to this kind of dark matter. And so now we're going to talk about a new mechanism which has a large viable parameter space and goes beyond the Grease-Kamienowski bound. So that brings me to filtered dark matter. Any questions on the introduction? Okay, so here we're going to present it in the sense of a toy model. It could be part of a more complete model, but we're just introducing the minimal fields that we need to describe the mechanism. So these are new fields. We have a new scalar particle phi and a new fermion chi. And the phi is going to interact with the standard model Higgs field through this quartet coupling. And then we assume that it has some kind of potential. We're going to assume that this potential gives rise to a first order phase transition, and in particular one that has a large order parameter, so it has that's larger than the temperature at the time at which the phase transition happens. So then this term here, we haven't written down a mass term for the chi particle. They're both standard model gauge singlets, by the way, the phi and the chi. We haven't written down a mass term for the chi particle. It may be there, but we assume it's much smaller than the other scales that are going on here. And then we see that when we have a phase transition, this interaction term, this Yukawa term, you get a term that has a VEV for the phi, and this leads to an effective mass term for the chi particle. So that's exactly like the Higgs mechanism for standard model fermions, but here applied for these BSM particles. So now we come to a picture of that phase transition. We have the scalar field has a non-zero vacuum expectation value in the blue. So that's kind of the new phase. And the old phase is on the left with 0 expectation value. And the bubble wall is moving to the left with some velocity v. And we're saying that the chi particle is essentially massless here. It may have a small mass, it doesn't really matter, but very light. In that phase, then dark matter is in thermal equilibrium through phi, and that's in thermal equilibrium with standard model through the quartic interaction. So all of these particles in thermal equilibrium with each other, they will have a common temperature. And there would be typically orders of magnitude too much dark matter if this chi were just to, if all of these chi particles were to survive until today without anything else happening, then there would be far too much dark matter. Thermal freeze out is one way of reducing the abundance of these chi particles. Here we'll talk about another way. So that's in the massless phase. In the massive phase, the chi gets a large mass, and this process is out of equilibrium on the right-hand side. So any chi particles that pass to the right-hand side can no longer be annihilated or created or annihilated. So we can then look at what happens when the chi particles interact with this barrier, with the wall. So the ones that have large momentum, momentum larger than the mass difference between the two phases, then the kinetic energy gets converted into rest mass energy. They can pass through the barrier, and their momentum is just reduced on the right-hand side. Whereas particles with a momentum that's smaller than the mass difference, the conservation of energy means that they can't get into the bubble. They don't have enough energy to convert into the rest mass energy that they would need to be in there, and they're reflected off the bubble. And so only the high momentum dark matter passes through the bubble wall, and then because we're out of equilibrium in this region, they then survive until today and become the dark matter that we observe today. And it's this kind of filtering out of the low momentum modes, which is doing the job of reducing the abundance. And this is why we called it filtered dark matter. So this is the cartoon picture. We do a simulation where we set up Boltzmann equations for the particles near the wall. We take into account their interaction with the wall and their interaction with each other in both phases, take into account annihilation and everything. And we have this is our one of our results for a point in parameter space. So we have the momentum perpendicular to the wall on this axis, and then the position, the distance from the bubble wall on this axis. We see the wall in the middle. We have some tangent function parameterizing the wall, moving at a velocity towards the left. The color coding is this curly A. This is the overabundance with respect to the equilibrium abundance. So the particle is very massive in here. The equilibrium abundance is much lower, so the abundance is quite different. And then this is kind of the overabundance with respect to the equilibrium abundance.
Yes, how important is the velocity here? And
Of the bubble wall?
yeah,
Not very, actually. We're pretty insensitive to the bubble wall velocity, as long as it's not super relativistic, as long as it's not runaway. So you need, I think, the gamma factor of the wall needs to be less than mass over the temperature. That's the condition.
So are you assuming the nucleation rate of bubbles is very low here? Because like otherwise you could have different bubbles converge on these.
Yeah, it doesn't matter for this. That's going to come into the next point. But here we just, as long as for each point in space, you have a bubble wall that passes that point, and it's going to filter out some of the dark matter particles. You don't quite see it here with the axis, but we see, so these are the low momentum particles which are reflected from the wall, like we had in the cartoon. And then we see we have this buildup of particles here. These then annihilate. So if you continue off to the left, not too much further, then the overabundance goes back down to no overabundance as the factor becomes 1 again. So you get like very close to the vicinity of the bubble wall, like an increase of the abundance of the Chi particles because they're being reflected, and then annihilate with each other, go back into the standard model plasma and disappear. So here we just need that the bubble walls cross all points in space. It doesn't matter on the configuration.
Does it matter whether you have like thin walls versus thick walls for the phase transition?
No, that doesn't matter. Not for this.
Sorry, the particles that scatter and like don't get in, like can they slow down the bubble, like there's some kind of friction or like
Yeah, well, sure. There'll be some friction from there. Here we're taking a phenomenological description of the phase transition, so we're not fully modeling everything. We're not computing the bubble wall velocity.
I see.
So we're more or less assuming that the friction from the Chi particles is subdominant to other sources of friction of the phase transition, and so the bubble just goes unimpeded. But we've kind of seen that it's the amount of dark matter we end up with is independent of this velocity, as long as it's not a runaway bubble and we don't have super relativistic speeds. So even if the velocity is changing in response to the Chi particles or whatever, then that doesn't actually affect the final dark matter.
Maybe you said it, I mean, but like you assume like a thermal phase transition, or it's like quantum, like it's like all three, or like the bubble nucleation. It's
I'm not sure it matters which
Okay.
one we choose.
I guess for the initial velocity of the bubble would matter, because if it's thermal,
Yeah, potentially.
like
Well,
what I
like
mean
I
is
say
that,
again,
what I
kind
mean
of-
is like that nucleation, you assume that when the bubble is nucleated, the velocity is 0 of the bubble, and then it grows.
So I mean, we're not very interested in
Okay.
exactly what happens at nucleation, just that it reaches some terminal velocity that's not too fast.
The mass of the Chi's does not affect the mass of the phi, even if it's larger. Doesn't do it. Is there a way to stabilize the mass of the phi? Like in the Higgs model, we don't know why. I mean, why it's 120 something, but here, why doesn't change? Doesn't run.
We've got that kind of like loop corrections.
Yes,
of the
yes,
Chi
yes,
particles.
because it's very massive, the fermion.
I mean, it's okay, a factor of 30 heavier than the mass of the phi. Okay, so here we just had a phenomenological description of the phase transition, so we didn't do we don't have like an explicit potential here.
Yeah.
So we didn't do a full modeling of corrections to the scale.
Yeah, one loop factor is
Yeah.
okay.
Right, yeah.
Slightly more than one loop factor, but not that much.
Okay, and so we then scanned over the parameter space, taking into account all of the constraints that we need and moving in and out of equilibrium in the right places and so on. And then because we're coupling to the Higgs, then we get some mixing and you generate a direct detection process through this diagram. And we can then cast our parameter space on the typical direct section, cross section versus dark matter mass plane. And so we have the existing experimental constraints, at least when you write the paper. I think we're down further down now, and the neutrino floor in orange and yellow. And the purple region is where the filtered dark matter mechanism is viable, where it can produce the observed dark matter abundance today. So we see that there's this island here that's kind of walled out, almost walled out. But there's this big chunk down here, which is beginning to be tested now. And interestingly, it extends above the GK bound.
But why is it discontinuous like that? Like, why is there an island?
Yeah, because of the mixing that's going on here, there's like a tan theta thing, which leads to this funnel shape. And so there's a theory thing going on there. And then there's a bunch of other constraints that we put in for you. I mean, if the scalar is too light, you can just look at scalar production at colliders. And there's a bunch of constraints we put in that mean that this section's not viable on this toy model. But right, the takeaway is that this is a viable dark matter production mechanism that satisfies all known bounds. That goes into this plot, and it's produces a testable models of dark matter and masses above the GK bound.
Question. So if you have low reheating temperature, you will get the same.
We just assume that the reheating temperature is above the phase transition
But
temperature.
if you have say lower reheating temperature, which is much smaller than the mass of your particles, then you get the same effect. Question.
So when you say the same effect, you mean?
Well, you mean your effect is associated with the fact that the mass of these particles is much larger than the temperature at this particular moment. If I say that there were no temperatures larger than certain amount, and the mass of your particles is much larger than this temperature, then you will get the same picture.
Without any phase transition,
without any phase.
Yeah, I think then that would be a similar production mechanism. Yeah, I think you can do that. I think when you, I'm not 100% sure about this, but I think when you look at this, then you can actually, there is an effect, but you can produce particles that are like quite a lot heavier than the actual reheating temperature. And it's like from the Boltzmann tail. Yeah, you're really filling in the Boltzmann tail of the distribution. But yeah, I think you could.
But here you also have this void.
Yeah, no,
sure. Right. So it's kind of the same.
Yeah, I don't see any reason why you couldn't do the same thing.
Yeah, sorry if you already mentioned this. How do you get the right relic abundance in your model?
Right, so just by the amount that can kind of pass through and the amount that's reflected, like the relative abundances of how much can pass through, how much is reflected. This is fixed by like the mass over the temperature, more or less. So by tuning the mass for each dark, you kind of tune the dark matter mass.
And then I guess your momentum distribution initially is fixed just by.
It's an equilibrium. It's like a thermal distribution at the beginning. So that's these two diagrams here are in thermal equilibrium.
I see.
Thermal equilibrium. So you have a thermal distribution of chi particles.
So on the plot with the annihilation lines, would your line just be horizontal, I guess, because it doesn't depend on your coupling at all? Or vertical?
It depends on the coupling, like on the y-chi coupling.
Yeah.
Of the Ikawa coupling. I mean, the mass is proportional to y-chi.
Yes, sorry. Thank you.
So to Tony's question, if you want a simple formula for the abundance, would it be the standard freeze out abundance times this Boltzmann factor, like e to the minus?
No, it's very different to thermal freeze out. We have a simple analysis.
Right, but on the left, outside the walls, you have thermal freeze out, and then the fraction of that passes through.
Yeah, you basically multiply by the integrated Boltzmann distribution of like with momentum larger than the mass.
And that's not a simple Boltzmann factor, like
It's it's like you get the exponential suppression. It's like the tail of
suppression.
Yeah, it's the tail of a Boltzmann distribution. Sorry, of the thermal distribution. So in the paper, we do both a simple naive analytic estimate based on that kind of thing, and this more sophisticated numerical simulation, and finding that an order of magnitude that those two agree. But this takes into account more effects that we don't capture by this simply integrating the distribution. Okay, great. Thank lots of questions. This is great. Great. The next thing we did with this is sort of went beyond the toy model, upgraded it a bit, and introduced interactions which violate CP. I don't want to go into this model in too much detail, but the point being, so chi is again doing the same thing. High momentum modes pass through, low momentum modes are reflected, but we introduced the CP violating coupling with the scalar, which changes the couplings at the walls. So right-handed particles have a slight preference to be reflected, whereas left-handed particles have a slight preference to be to transmit. And introducing an extra higher dimensional operator we just put in to couple to right-handed neutrinos, we can then create a lepton asymmetry. And as long as this is happening above the electric phase transition, electric phallons can convert this lepton asymmetry to a baryon asymmetry. And so we showed through that. I don't want to go into too much detail, but you can do baryogenesis and produce dark matter at the same time in the same phase transition with the same degrees of freedom. Just introducing some extra couplings. Okay, same degrees of freedom up to some effect. We introduce some higher dimensional interactions as well. Because of the framework we used, it turned out we could only rely on our calculations when a certain coupling was large. So we only showed that we can do baryogenesis and dark matter at the same time in this upper region of parameter space. We have no real reason to think that it wouldn't work in the full parameter space, but just the setup that we used to do the computation wasn't applicable there. So we've only shown it here, and yeah, in the future we have it in mind to extend the analysis to the full region. But that was just very briefly that, yeah, it's very interesting that we can introduce some extra CP violating operators and basically do electroweak baryogenesis, but at this new phase transition and at the same time as producing the dark matter abundance.
So for this and also the previous plot, what's the temperature for the phase transition?
So the temperature is always about like a factor of 10 or so less than the mass. Okay. So it's in this, right, so you have some kind of cutoff. I forget exactly where it is, but because you need the phase transition to be above the electric phase transition temperature to be able to rely on the electric phallons. So there's some cutoff, but it's related to the mass.
What is the range of the right-handed neutrino mass?
What do we do? I think we might. I haven't written down here. I'd have to look back at what we do. I think we just pick a benchmark that's high enough and can be produced like neutrino masses through a type 1 seesaw or something. I think we do that kind of thing. I need to check back in the paper exactly what we do there, but I think we just pick a benchmark that works. But there's a bunch of free couplings in here, so you have quite a lot of freedom.
There is a neutrino floor.
Oh, here. This orange line. Yeah, this is maybe the better term now is the neutrino fog. And so this is where in direct detection experiments you'll start to see events that come from I think all from solar neutrinos, maybe some from cosmological neutrinos, I'm not 100% sure. But they look indistinguishable from a dark matter event in your experiment. So it's not actually a bound or anything. It just becomes much harder to do direct detection experiments to probe the parameter space below this line. It becomes much harder because you have an irreducible background from neutrinos. But there's like an active program at the moment about how direct detection experiments could push into the neutrino floor. So it's not like a hard limit or anything. It's just it becomes more of a challenge to do direct detection experiments. Okay, so that was the first part. Now we're going to move on to black holes. I'll give a brief introduction, but we'll see how the ideas we've been discussing naturally lead on to talking about black holes. So there's been a huge increase in the interest in black holes, especially in kind of my community, sort of BSM phenomenology, since the direct evidence of black holes. We've had indirect evidence for a long time, growing evidence, but I think it was really the LIGO-Virgo observations of black hole solar mass black hole mergers, which really sort of definitively said, yes, black holes exist, they're around us, and we should start thinking about them. This was followed up by the Event Horizon Telescope, where they imaged, I think this is M87 on the left and the black hole at the center of our galaxy on the right. These are not solar mass, these are supermassive black holes, but again, direct evidence of black holes. Around us. So those are solar mass and supermassive black holes that we know definitely exist. There's also reason to think about primordial black holes. So I'll mention some motivations for thinking about these at the end. So yeah, what are primordial black holes? Primordial black holes are ones that were formed in the first second of the universe, more or less. So the solar mass black holes that were seen by LIGO-Virgo, they could have resulted from supernova, from star collapse, and then you get solar mass black holes. We don't quite know where the supermassive black holes at the center of galaxies came from, but if there are lighter black holes than solar mass black holes, there aren't really compelling astrophysical production mechanisms for them. So one place that people think that they may come from, if they exist, is from physics in the very early universe, and then these are primordial black holes. We'll see some motivations for these in a few slides' time. But for now, we're going to talk about a new production mechanism for them. Like with dark matter, there were some existing production mechanisms. So collapse of density perturbations generated during inflation, that's the sort of favored production mechanism. But it's quite finely tuned. You need an inflaton potential that has certain properties that are kind of hard to engineer to be able to produce primordial black holes in this way. They could also be produced by the collapse of topological defects, by dynamics of scalar condensates. People have considered collisions of bubble walls during a first order phase transition. So there's quite an active community thinking about ways that PBHs could be produced. But previous work on these PBHs produced through a first order phase transition, they've just considered energy stored in bubble walls. But we realized that we could repurpose this dark matter production mechanism to be a PBH production mechanism, and focusing on the population of particles that interacts with the wall. This is the Chi particle that we've seen so far. So this is a kind of another way that a first order phase transition could produce primordial black hole. So we take the same kind of setup that we had before, but now we go to a region of parameter space where the Chi particles are not in thermal equilibrium in the high temperature phase. And so what does this mean? Previously, when the Chi particles reflected from the wall, they quickly annihilated back into the thermal bath and disappeared. But if that's not in thermal equilibrium, then these particles are just going to build up in this region, and then they're not going to have anywhere to go. So then you need to change your analysis. You can't just do this sort of one-dimensional simple thing of the wall, just like going through the whole universe. But you have to think about bubble walls colliding and like in 3 dimensions, and the time evolution of this. So now we're kind of a late stage in the phase transition where we've got several bubbles which are coalescing and form an approximately spherical region, which is shrinking with some velocity. And we have these Chi particles. Again, the high momentum ones can pass through, but the low momentum ones are just reflected in this sort of shrinking bubble region. And we wondered whether the buildup of Chi particles in here, just the energy density stored in the Chi particles, whether that could become large enough to lead to PBH production. And so we did a similar thing where we set up Boltzmann equations in this now pretty complicated setup. And we're then able to track the energy density of this population of particles. So we were yeah, reflecting them off the bubble wall and okay. Skipping the bulk of a ton of stuff here, we can go straight to the results, where here we look at the energy density stored inside that region as a function here, it's of the bubble radius. So as the bubble shrinks with time. And the two solid lines, these show parameter choices such that we can produce primordial black holes. So essentially the energy density, the energy inside a region, the size of that region becomes smaller than the structural radius of that energy, and then you can't stop a black hole from forming.
And I mean, presumably it gets very hot in that region right before that point, right? So it doesn't back react on the bubbles in that case.
So by hot, you mean these chi particles are?
Yeah.
It depends a little bit on the velocity of the wall and like how many times the chi particles bounce around. So the wall is coming in, each time they bounce, they pick up a little bit of energy, like a bit of energy is imparted from the wall on the particle. So if they bounce around a lot, then they heat up. But if this velocity is like a significant fraction of the speed of light, then the particles only bounce a couple of times, a few times before you reach this point of collapse, and you don't get a huge heating effect. But we took account of that, I mean, we tracked the momentum of these particles.
And you're far away from the generacy pressure, these fermions. Like at some point, but then I mean you're close to black hole densities, right? So do you form a chi neutron star before you reach black hole densities?
The answer is no. I think I can't remember exactly if there's an interesting reason why not, or I mean, we took this into account. Yeah, I don't have in mind exactly the conclusion of that part of the paper right now. We can talk about it later if you like. But we took it into account. And
You checked it. Okay. Sorry, final question. 5 bubbles colliding and pinching off region should be unlikely, right? I know this is a cartoon, but is the main region 3 bubbles colliding and pinching off a region?
So right, so something I kind of skipped over here. This is compared to the Hubble radius at the time. So we need a large bubble. We need a bubble that is sort of the size of a Hubble radius at the time, or a little bit larger.
And by bubble you mean complement.
Right, yeah, sorry,
Okay.
It's a pocket, I think the proper term, pocket. And then we need that for the whole time that it's collapsing, no other bubbles nucleate inside. So if another bubble nucleated inside, then that would kind of break up the region and stop you collapsing all the energy density down to a small enough region. And so we've done some calculations to, okay, let me go to the next plot and I'll come back to it. So the next plot is kind of quite a generic plot. This is the mass of the PBHs that you form along the bottom in solar masses in grams, along with the temperature at which the phase transition is happening. And you can basically correlate the temperature with the mass just by saying it's 1 Hubble volume's worth of energy that's collapsing into a black hole. And you get this rough correlation. But the extra thing that we're adding here is this P. Oh yeah, I should say this y-axis. This is the energy density in black holes, which is often phrased as a fraction of the energy density in dark matter. So this line across the top, if you lived up there, then you'd have enough primordial black holes that they would all constitute dark matter. The gray regions are various constraints. And if you're down here in the white region, then you can have primordial black holes as a subdominant component of dark matter in the universe. And now this P, this is the probability that 1 Hubble volume, so if you have a bubble that's a Hubble volume in size, what's the probability that no other bubbles nucleate inside of it? So we see to be like in an interesting region, say here that we're forming PBH dark matter. We just need 1 in 10 to the 15 bubbles to not have another bubble nucleate inside. So we actually need very few of these regions to end up producing primordial black holes. And we've done some rough calculations of the kind of beta parameter you need of the phase transition such that these numbers are viable, and it all seems quite reasonable.
So you also have some bubbles presumably that come in, but they don't quite reach enough of an energy density to actually become a black hole.
Yeah.
So now you just have really, really large chi overdensities. And those will presumably stick around until late times, like I don't know if you make them decay or whatever, but there'll be some fraction of your dark matter too, right? But
They
here,
may or they may not, like we still have, so even though you're out of thermal equilibrium, when you've compressed them, the particles can then annihilate away. And then there's a mechanism by which you're compressing them, you wait long enough. If you wait just one Hubble time, they don't annihilate, but if you wait many Hubble times, many of them will annihilate away down into standard model particles in the end.
so you assume there's basically no chi.
So we
at
assume
late
that
times.
there's none
Okay,
left.
okay.
But yeah, no, there may be interesting things where you end up getting kind of Fermi bubbles alongside these primordial black holes. This is the slide where we have some of the motivations for thinking about primordial black holes. So primordial black holes could potentially be dark matter up here. The Ogle Space Telescope, this is looking at like lensing events. It's seen some possible candidate lensing events that some people think may not be associated with like free planets or something. And so there's a QVH interpretation of those. And like I mentioned, the supermassive black holes at the center of galaxies. We don't have good models of where they could come from, but so they could have been primordial from a low temperature phase transition, and yeah, just produce these very, very massive black holes, which are now at the center of galaxies.
What kind of mass functions do you get for these PVHs?
We haven't computed that yet. No, that's something we're interested in. So yeah, there's a whole set of stuff we'd like to do with this. We don't have explicit phase transitions. We sort of have a phenomenological model of the phase transition. The one thing we'd like to do is really have like an explicit UV model where we can compute the phase transition properties and the resulting black hole mass distributions and so on. But that's to come. Okay, any other questions before the final section? It's kind of in thirds.
Sorry, I don't know, what is this overclosed universe? What's that?
Yeah, well, so overclose the universe up here. So the primordial black holes that we form, they act exactly as dark matter. And we have this, like I said at the beginning, we have this very good measurement of how much dark matter there is in the universe. And so if you have some mechanism which produces more energy density in primordial black holes than the measured amount of dark matter, then you violate that experimental constraint, and that's what it means to overclose the universe. And so
Before is, but isn't it during the radiation domination, this overdensity should be really flat, this in the end? No?
so during radiation domination, the overdensity of what should be flat?
The contact matter should be really flat, and after this equality time, it pumps up a little bit.
This is the background density. It's not the, this is not the perturbation density.
Oh, okay.
Okay, next. Okay, there's quite a lot I still want to cover in the end, so let's go back, but feel free to ask me questions about anything you've seen. Let's go. Exploding black holes. Okay, so far I've just been talking about black holes as kind of like static objects, but theoretically they're expected to Hawking radiate. And the cartoon picture here is the empty space isn't empty, you have virtual particles always popping in and out of existence. If this happens near a black hole, then one can fall into the black hole and the other one can escape. So we shouldn't think of black holes as black, but we should think of them as having a temperature and constantly radiating particles. So this is Stephen Hawking radiation and the temperature of a black hole. So you can compute the particles that are emitted from a black hole. So this is the flux of particles that are being emitted with identity I, and this P is for primary. It's almost black body. There's a gray body function here, which you can compute, which basically tells you the deviation of the spectrum from a black body. And the black body has a temperature in which is like inversely proportional to the mass. So this is kind of quite important. Okay, well, let's go to the next step. Okay, so black holes are always radiating. We can compute the rate at which they radiate particles. And yeah, they radiate all particles basically with a mass less than the temperature of the black hole. So they're radiating. So this is conservation of energy. Tells you that as they radiate energy, where does that come from? It comes from the mass of the black hole. So the mass of the black hole goes down as particles are radiated. This alpha function is basically just the sum over the energy of all the particles that are being radiated. So we have a black hole, it's radiating particles, its mass goes down. As its mass goes down, its temperature goes up. Its temperature goes up, it's roughly black body, so the flux increases. That means the rate that it's losing radiation increases, so the rate of mass loss increases. And so the rate that the temperature goes up increases. You have this runaway process, this is why we call it an explosion, because it's really a runaway process where as it radiates, it loses mass, it heats up, and it gets even hotter and hotter and hotter and hotter. So that's a black hole explosion. The black holes that we've seen so far, the solar mass black holes and the supermassive black holes, the temperature is inversely proportional to the mass. They're so massive that the temperature is so cold that they're not going to explode anytime soon. In fact, their temperature is currently both lower than the CMB temperature. So they're not in a vacuum, they're net absorbing CMB photons rather than emitting them. So they're kind of gaining mass from CMB photons and accretion. So they're not going to explode anytime soon. You have to kind of wait to the heat death of the universe until then they finally explode. But primordial black holes, which could be much lighter and so much hotter, could be exploding today. That's what we're going to think about now. Any questions about exploding black holes? Okay, great. So this alpha, this is the sum over all of the energy that's being emitted. And there's a factor of m squared pulled out basically because then when you plot this alpha as a function of mass, it's flat until you hit thresholds of particles. So a cold black hole is over here. And then when we get down to 10 to the 14, 15 grams, its temperature goes above the QCD phase transition and you start emitting in pions and so on. The number of degrees of freedom that you can emit into sort of gives you these steps. We then have the B quark and so on, electron leakage bosons. Okay, so we're emitting all particles that are, right, okay. And so this is basically the statement that the black hole is emitting all particles with a mass less than its temperature. So these are the particles that you're emitting into. As you go down in mass, you go up in temperature, and you can emit into more particles. We're always emitting into the photons. So there's some just primary flux of photons from here. But there's also a secondary flux of photons. So especially when we go past the QCD phase transition, then we say we're emitting ions, which decay almost all of the time into photons. You have, or maybe you're emitting top quarks and you have final state radiation, and you have all of this. Like at the LHC, you get this this mess, hadronization and final state radiation and so on. And then this is called the secondary photons, and you can compute these. We used Pythia, so LHC software that computes these functions, the amount of photons you get from some initial top quarks or whatever. And so you sum over all of the different species of primary particles that you're emitting, and then you find the probability that a primary particle of some energy is going to convert to a photon of a different energy, and then you integrate over the energy of all the primary particles, and you get some spectrum of secondary photons. So from a black hole of different masses, here 10 to the 12, 10, 8 grams, you get a spectrum of primary energies, which are the dotted lines, and then this big tail of secondary photons. So you get these two big contributions to the photon flux from an exploding black hole. So that's all theory so far. On the experimental side, there are experiments now which are looking at space, searching for exploding black holes. So the one that sets the best current limit is the Hawk experiment. This is a bunch of tanks of Cherenkov detectors, tanks of water, up in the mountains in Mexico. And they're sensitive to high energy gamma rays that come in, interact with an atom in the upper atmosphere, create a shower, and then you can detect that shower down through the Cherenkov radiation. Okay, and so this is a gamma ray observatory. It's looking at a large portion of the sky. It has a large sort of angle that it's looking at, basically all the time. So it doesn't need to point at particular places. And that's one of the things that makes it so strong for looking for exploding black holes. You don't know where one of these may go off. And this telescope is just always looking at a very large solid angle of the sky. Okay, so that's all kind of like standard story so far. And then we made the observation that if there were BSM particles, that's going to change this alpha function.
Before this, can I just ask, because people look for a gamma ray background from evaporating black holes.
Yeah.
Right, which is kind of the continuous before they explode. Yeah, so and there's limits on primordial black holes that way, right? And so those limits are
We'll get there. We'll
okay,
get there.
okay.
Let's do the exciting bit first before we do the boring bit.
Okay.
Actually, they're both exciting in different ways, but yeah, we'll talk about that. Let's just imagine for now that we have a hope of seeing a black hole exploding. If we do see a black hole exploding, then what can we learn from that? That's kind of the question that we asked here. And we made the observation that BSM particles change this alpha, because that was the sum over all particles that are being emitted. And so if you have new particles there, then they change alpha. And there's the really interesting observation that it's independent of any Yukawa couplings or gauge couplings. The way they couple to the black hole is through the stress energy tensor. So this is exactly a way of testing for particles with, I mean, all particles, even if they don't have a non-gravitational interaction with the standard model. So they would still change alpha, and that would change the black hole evolution, and so change the photon spectrum that you would see in principle. And we asked the question, if Hawke saw one of these, what could you actually infer? We looked at a model of a dark sector, which is completely secluded from the standard model. So there's only gravitational interactions with the standard model. And this dark sector consists of n copies of the standard model particles. So we're going to have different values for n. That's like 100 degrees of freedom. And we imagine that all at a common mass scale we call lambda dark sector. So how would that change alpha? If we have, so here we have one copy of the standard model all at 10 to the 5 GeV. So the alpha would follow the standard model one until the temperature gets to 10 to the 5 GeV, and then it would more or less double because we're turning on another 100 degrees of freedom. Or you can imagine there's 1,000 degrees of freedom in the dark sector, 10 copies of the standard model that turn on at a lower energy. But the point is that for all of these different dark sector models, you change alpha in different ways. And this is observable if you saw the photons from the exploding black hole. So we did the analysis at Hawke and basically said how many if you saw a certain number of photons, what could you probe? Which of these models could you probe? And so if you saw about 200 photons, which would correspond to a distance of about 0.01 parsecs, then you could probe a dark sector containing one copy of the standard model up to mass scales of 10 to the 5 GeV, 100 TeV. So, I mean, I think this is really, really cool. It's not a crazy number of degrees of freedom. It's one copy of the standard model. And you can probe up to 100 TeV. This is beyond the LHC, far beyond the LHC energies. And there's no other constraints on here because this is really a model that doesn't interact with the standard model. It only interacts gravitationally. And so there's no real other way to probe this kind of model.
What mass is that?
So,
Would it be easy to separate this from, say, like gamma ray bursts or other gamma ray observations?
yeah, so speaking to astrophysicists, most astrophysical events have the way the photon spectrum goes. It gets harder, but then it gets softer afterwards. You have this afterglow from almost everything except these. And so that's how we would think about differentiating this from astrophysics.
And what's the mass of the black hole that you need here?
The mass is changing, it's exploding, right?
Right, but
so we look at like the last 1,000 seconds.
let's say where the bulk of the energy is emitted. I guess.
So I mean, it's this basically I mean, it's this kind of standard. It starts off a primordial black hole that was formed with, I think it's 5 times 10 to the 14 grams.
Okay, there is.
And so, yeah, and so its temperature is about 100 MeV. And so you're thinking, I guess you're thinking about the extra, the gamma ray background indirect constraints.
I was worried about the distance because it would be in the solar system. And if it was too massive, then maybe we could detect it gravitationally. But if it's only 10 to the 14 grams or so, then
yeah,
that's like an asteroid. That's very difficult.
I think whether or not this is in the solar system depends a little bit on your definition of where the boundary is. No,
It doesn't have to be the dark matter, it could just be like very rare.
No, but if it's if it's 10 minus 3 parsecs, then
right, yeah, then
it would perturb the planetary orbit.
Right.
but it's very light.
Yeah.
So it's much lighter than an asteroid.
What happens if you have like many light degrees of freedom, for example?
Yeah, so and naturalness is really interesting to think about in here, no? Because there you've got 10 to the 20 new degrees of freedom. A black hole explosion looks vastly different. And we think in fact most of the energy just goes into the dark sector and you don't see it. Here you have to have photons to see. But that's something we're interested in about, like, yeah, how extreme can this get in different models? We haven't really looked into it too much yet.
Oh, sorry. So for your final state,
We're just looking at the photons that we get.
Do you have any sort of good natural models that give you these 10 to the 14 gram primordial black holes at early times, or is it just you're just putting them there?
No, we're just putting that. I mean, as good as any other. I mean, any PVH production mechanism would, I think, can.
Well,
Give them
they would have
this
to be very
mass
light, like if they're too light, right, then in the very peak, then they would decay too fast, presumably, to be seen.
Yeah, right. So we had this plot, and so the ones we're talking about have a mass around here. So we're formed probably at a scale around 10 to the 8, 10 to the 9 GeV. And then, I mean, that's just the ones that we're talking about. So any PBH production mechanism that was active at this time in the universe's history would be producing the ones that would be exploding today. But to my mind, just, I mean, hugely exciting and hugely powerful. There's no other ways of testing these models, and you don't need that many photons to have a great probe. Okay, any questions about this before we go on to the final part of this? Good. Okay, so this comes back to your question about, here we've just thought about, okay, let's imagine we're lucky enough to see one exploding. But then what's the chances that we see one exploding? And there's criticisms that, you know, it's very unlikely that you'll see one exploding. And the argument for this is, so like I said, this Hawke experiment puts the current limit on the number of black holes exploding per cubic parsec per year is like 3,000. So they haven't observed any yet, and this is the limit that they can place on the number exploding in the vicinity of Earth.
Our galaxy is only 20 kilobytes each direction.
Yes, right. No, but we really need to see them like within a parsec or something. If they're beyond a parsec, then we don't really get any photons from an exploding black hole. Not high energy ones, not that we can differentiate from background. They just kind of, yeah. Okay, so so this is the argument against observing one. So I've hopefully convinced you that it would be very exciting if we did observe one. That's the good news. The bad news is maybe we're never going to observe one. And there's an argument against why we think we should ever observe one. So we've just kind of talked about one PBH exploding, but if you hope to see one, then you expect there to be a population of primordial black holes out there, most of which are not exploding today. And so they all end up having a temperature around, I mean, if you have some kind of typical mass distribution of black holes centered around the mass of the ones that are exploding today, then they will have a temperature around 100 MeV. And you can look at, they would be contributing a flux of 100 MeV photons that you would be able to observe. So this is again this fraction of the energy density in primordial black holes compared to dark matter against the mass. And there's this very strong constraint from looking at these 100 MeV photons and the fact that you don't see any. So this FPBH has to be around 10 to the minus 10. There's also a slightly lower mass as a similar thing, looking at CMB anisotropies. If you inject too much energy anytime after the CMB, then it affects the CMB anisotropies. So these are quite strong constraints at a level of 10 to the minus 10 in this FPBH. And if you assume a relatively motivated mass distribution, then it tells you the explosion rate that you should expect is around 0.01 per cubic parsec per year, which is many orders of magnitude lower than the Hawke limit. And you, in fact, if it was this, so the maximum allowed on this argument, that you'd expect to see one event every 10 to the 5 years. So that's much less exciting. So it would be great if we see one, but we have to wait 10 to the 5 years to see one, is the argument. But this assumes that primordial black holes are Schwarzschild, so they have no spin and they're not charged. It's a Schwarzschild black hole. And it doesn't account for any BSM. This is just thinking about standard model particles in nature. And so now I'm going to present, going beyond these two assumptions, a mechanism where we can get a large burst rate today. So we go beyond the standard model. We introduce a new U1. So this is just like a copy of QED. We've got a dark photon, which is either massless or very light. It's very difficult to detect. And we have a dark electron, this is LD, with a mass MD. So this is just a new dark QED. We're going to assume that ND is very large, so like 10 to the 10 GeV. And so then this model is very, very difficult to detect. So we're kind of safe from any constraints on the model here. There's no constraints on this model, not with this huge dark electron mass and a massless dark photon. So that's one assumption. And then we assume that there's some formation mechanism of the primordial black holes, which I'm not specifying, which means they form with some dark charge. And that's okay, that's the ingredients that we need. So when there's dark charge in the game, we have this mass evolution of the primordial black hole, follows this first formula, but now these gray body factors also depend on the dark charge. And then you can track how the charge evolves with time, according to this formula, which I'll tell you what this encodes in the next slide. But you basically have a couple differential equations that you can solve to track the mass and dark charge with time. So we solve those differential equations. We have the mass in blue. So we start with one that's almost 10 to the 13 grams. And the dashed line is if it was Schwarzschild. So if it was Schwarzschild, then it would just explode after around 10,000 years after the Big Bang. So that wouldn't be any good. We wouldn't be able to see that. But if instead it starts with some dark charge, that's this QD star. A charged black hole is called a Reisner-Nordstrom black hole, so that's this Rn. Okay, so we start with some small dark charge, which isn't crazy to expect from some PBH production mechanism that involves these fields. As the mass drops, now this QD star, this is the charge times the Planck mass divided by the black hole mass. So as the black hole mass goes down, this QD star goes up. So the black hole mass is coming down. And the way we're parameterizing this QD star, minus log 10 of 1 minus QD star, this basically counts the number of nines in QD star. So here at 5, this is 0.99999. It's the QD star. So it's becoming very close to extremal. So this QD star, it can't ever become exactly 1. There's Reisner-Nordstrom black holes have 2 different horizons. If it goes beyond 1, then you would have a naked singularity. And you can't have that. So what happens is, as it loses mass, this extremality parameter QD star gets closer and closer to 1. And we see that the temperature of a Reisner-Nordstrom black hole, it's not just 1 over the mass, but you get this extra factor that has a 1 minus QD star squared. So as this gets close to 1, the temperature drops. So we see the mass comes down. As the mass comes down, QD doesn't change, but QD star goes up because of the mass. And so that's here, QD star shoots up. And then that kind of like that halts the explosion. It was beginning to explode. Orange is the temperature. It was beginning to explode, but then it becomes quasi-extremal and that cools it back down again. And the temperature then drops for quite a long time. So from 10,000 years to, it's going to be until today for this choice of parameters. The black hole is just kind of quasi-extremal, it's metastable, sitting there with basically a constant mass, and its temperature is very cool. It's basically not emitting. So the other effect, which I haven't talked about yet, is the dark Schwinger effect. So as this QD star is going up, the electric field, dark electric field near the surface of the black hole gets stronger and stronger and stronger and stronger. And at some point, it becomes energetically favorable to take energy out of the electric field and create a dark electron-positron pair. This is the Schwinger effect, but now for our dark QED. And it turns out this turns on very quickly. When this happens, the black hole discharges very quickly. It stops being quasi-extremal, loses all of its charge, and so essentially then becomes Schwarzschild, and it then very quickly follows the Schwarzschild-like final burst. So this is a way that we can have a population of lighter black holes that spend most of their time cooler than you may expect. That's true. It's still around 100 MeV. But the main point comes from them being lighter. So then when we look at the indirect constraints that we get on this population of black holes, these two curves from the extragalactic gamma ray background and from the CMB, say that we take this, which one do we take? C, I think is the one we were looking at before. These two spikes that you get, these are the indirect constraints that you would get from a population of these quasi-extremal dark charged black holes. Right. We see here that they're much sharper than these peaks. And it was because in this mechanism, the lifetime is more sensitive to initial mass than in the Schwarzschild case. Okay, so here we're assuming we're showing these constraints, and this is how these constraints are typically shown for a distribution of the particles for a population of the particles that all have the same mass. That's not what you would expect to form. You would expect to form a distribution of particles. So you can rephrase these in terms of a distribution of masses. And we do that. And then this is the BSM parameter space. So we've got the dark electron charge, and then these are contours. Sorry, dark electron mass and contours of the dark charge. So this is a way of presenting the BSM parameter space. The color coding is the maximum possible burst rate. And at the top in this blue region, that's where the burst rate is this 0.01 per cubic parsec per year, which you would typically get from the indirect constraints. But then when we see that when we go down in this parameter space, we can get much larger burst rates. And in fact, the main reason for this is because these black holes are lighter than those. So we see that we reduce FPDH a little bit by 2 orders of magnitude. But then also these are lighter. So to get to the same energy density, they're much more numerous. So you go down 1 to 2 orders of magnitude, say, in mass. To get the same FPDH, you have 2 orders of magnitude more of them. The number density is much higher. And that leads to all those 2 effects together, but it's mostly the second effect, leads to a possible much higher burst rate of around 10,000 per cubic parsec per year. And these yellow contours, these are the probability of observing one, assuming the population which saturates the indirect constraints, the probability of observing one at Hawk in 10 years of data. And that's what we picked. And we're assuming a reasonable mass distribution here. So doing all that, we see that the probability of an observation at Hawk can be over 95% in this mechanism. Okay, I'll go through the conclusions and then we can have the other standing questions. Okay, so we started off with a novel dark matter production mechanism. And we saw that that could be extended to also give novel baryogenesis mechanism at the same time. That train of thinking led us on to a new primordial black hole production mechanism. And okay, that got me thinking about exploding black holes. And we see that you can have like really great constraining power on BSM physics from an exploding black hole. And while you may think these indirect constraints mean that you will never see one, at the end we've demonstrated that it's conceivable to observe an exploding black hole. So I think my position here is maybe not that we should expect one in the near future, but that we should definitely be prepared for the possibility of one. So we should make sure the experiments are well prepared for the potential of seeing an exploding black hole. And we should figure out how to best make use of that observation. Okay, thank you. Stop.
We've had quite a lot of questions. If you want to go, please go ahead. But yeah, otherwise, yeah.
I have one more on the end with the Schwinger pair production. So you showed before, right, that the mass saturates because it's quasi-extremal here. And then the charge keeps going slightly closer and closer to extremal, but it's only changing by a tiny amount. So the electric, it's near stationary, right? So I don't quite understand how the Schwinger effect turns out so suddenly, or is it just so slow and it's logarithmic axes that I'm. Yeah, why does it turn on at the end? That's what I'm confused about.
So you have this exponential behavior in the
Yes.
Schwinger effect.
Okay, but that really means you're exponentially sensitive to the mass of the dark charge, right? It needs to be very close to the eventual saturation temperature. I mean, anyway, depending on this exponential. If MD was twice as high, then it would never explode, and if it was half as massive, it would.
Yes, for these exact initial masses and dark charges. But what you really expect is a distribution in initial masses and a distribution in dark charge masses. So you can think of some like Gaussian in the initial dark charge space.
Mm-hmm.
And then the ones that are exploding today, there's a line in that space.
Right.
Which are the ones that just happen to be exploding today.
Right. So for fixed dark electron or whatever, there's only a small slice of primordial black holes with just the right mass charge combination that would explode late. All of the other ones would explode early, or
half would explode early, half would explode much later.
Yeah.
But this is exactly the same.
And then like some sliver would explode at just the right time.
But that's exactly the same for the Schwarzschild case. There's like one exact mass which is exploding today, half have exploded already, half are still to explode.
Okay. Okay.
Can you say just a little more about how you produce this charge distribution? Like naively, if I took your own PBH production mechanism and I gave the chi's some dark charge that gets squeezed together, that blob is effectively neutral, right? I'd probably expect all my PBHs to be very neutral. Like what model would give me sort of a wider distribution of dark?
So one cheap way is having like an asymmetric chi thing at the beginning.
Okay.
So have some asymmetric dark matter type thing where you form some asymmetric dark charge. I mean, it'd be interesting to tie this to baryogenesis. And so the baryon asymmetry could be the other half of the dark charge asymmetry. That's kind of like the cheap, easy way of doing it. Another way of doing it is it turns out just through Poisson variation. So then not all of the black holes are going to be exactly neutral. You'll have some that have a few more and some that have a few less. And it turns out the numbers aren't so far away from this 0.01. I think 10 to the -4, 10 to the -5, something like that, is what you just naturally get through Poisson variations. So while you may think you need a huge